Welcome to Part 3 in the module on Android support for programming concurrent and network software. In Part 1 of this module, we presented an overview of the Android layered software architecture and some of the key framework components it provides to applications and higher-level services. We then described the Android mechanisms available for networking. In other words, internet communication from Android devices out to the cloud or servers, as well as local inter-process communication between different processes and different activities or services on the same device. In this part of the module, we're going to present an overview of the Android mechanisms available to implement concurrent applications that can process threads simultaneously via multi-threading, as well as be able to synchronize their interactions. Again, no real source code here, a couple interaction diagrams and so on, but we'll cover the programming later. So let's first start by talking about an overview of Java threading. At the core of the Android concurrency mechanisms are plain old Java threads. And there's a couple different ways to look at Java threads. There's a conceptual view where Java threads provide concurrent programming of computations that run simultaneously within a process. There's also an implementation view. If you dig a little deeper, you'll see that each of these threads has their own stack, has their own set of registers. Those are unique to each thread. And then they also share certain information with other threads running in a process. Things like the heap to allocate memory, static data, global data, and so on and so forth. If you take a look at this URL, you'll find out more about processes and threads in Android. So let's talk briefly about how you use Java threads. You probably are familiar with this already, but if you don't have a lot of background in Java threading, let me give you a quick recap. So in Java, all threads have to be given some code in order to run. And you typically do this one of two ways. You either basically extend or inherit from the thread class and override its run hook method, or you implement an interface that's the runnable interface and override its hook method. Either way, you define a method called run. And this hook method is then started automatically by the runtime system of Java and Android when you call the start method on a thread instance. And what will happen there, you typically allocate a new thread, you call start, and then the run method starts to run. And that run method can run concurrently with other things that the thread that called it may choose to do. And they can do a whole variety of different kinds of things. One could be blocking, doing network communication or accessing files. The other could be sitting and taking events off of the event loop and displaying them, and so on and so forth. When the thread is done, when the thread that's been started is done, its run method will complete. And various things can happen. The main thread could join with it, or the thread could just evaporate at that point. And when it's all finished, that thread disappears, its resources are reclaimed, and the program continues, of course, concurrently with other threads that are going on. And naturally, you can spawn lots of other threads, and they can be doing other things in parallel to all of this. Here's a little view of a state machine that illustrates the various states that a Java thread can be in. When you create a new thread, the thread has been created. When you call start, it becomes runnable. At some point, the Java and Android thread scheduler will select the thread to run. It is now running. It can continue to run doing various computations. It could go to sleep, which would make it in the sleeping state. It might go ahead and wait on a monitor condition, in which case it'll be waiting until it's notified later. It could block on some kind of guarded resource, like a mutual exclusion lock or a synchronized section and so on. These are some of the various states. It can be preempted by the system and so on. So these are the various states that a Java thread can be in Android while it's running. Synchronizing threads in Android is fairly straightforward because of the way that Java threading handles synchronization. Typically, the most common way of doing this is to add the synchronized keyword to a method that you want to have become what's called a critical section. And so what will happen here is it will then ensure that the runtime system of Android and Java makes sure that only one synchronized method at a time is active in any given object. And here's just a little code snippet that shows that only one method will be running the on location change call, even if it's multi-threaded. Under the hood, this way of arranging things is called the monitor object pattern. And the monitor object pattern basically makes it possible for objects to synchronize at method call boundaries and then provide ways to be able to wait and notify each other, the different threads, in order to do various kinds of collaborative scheduling. If you take a look at my website, you'll see a pattern description of the monitor object pattern, which also appears in the POSA 2 book and many other places as well. There's also a broader range of Java synchronization mechanisms available in Android through the Java util concurrency package. You have things like locks, semaphores, conditions, reader-writer locks, and so on. And if you take a look at this package summary, you can learn more about the various kinds of synchronization mechanisms that work with Java threads in Android. There are also some things in Android that go above and beyond what you would find in vanilla Java and vanilla Java threading. These are some idioms and concurrency models that are specific to the way in which Android handles various kinds of activities. For example, Android's user interface has several design constraints that affect the way in which concurrency is used. One of the design constraints is that an application not responding, or ANR dialog, is generated if an application's user interface thread doesn't respond to user input within a fairly short period of time, typically 3 to 5 seconds or so. Likewise, non-UI threads can't access the UI toolkit, the UI classes and objects and methods and so on, since it's not designed in a thread-safe way. If you take a look at this link, you'll find out more about application not responding, or ANR dialogues. So because of these constraints, Android supports various concurrency idioms, where idioms are basically context-specific patterns. The context here is Android programming, that allow long-running operations to take place in background threads and then communicate in various stylized ways with the UI thread, the user interface thread. And we're going to talk about two mechanisms here briefly, which we'll then explore later in the course with more examples. We're first going to talk about async tasks, and then we're going to talk about handlers, messages, and runnables. What's an async task? An async task is actually a framework that provides a structured way to manage work that involves background threads that are running for long periods of time interacting with the user interface thread. And the basic idea here is to allow the background thread to run blocking or long-running operations without causing the UI thread to incur an ANR, an application not responding dialog. To use async task, you have to inherit from the async task base class. And then you have to go ahead and override certain hook methods. We'll talk more about this in later sections when we talk about frameworks. We'll talk a lot about async task, and we'll show some examples in other parts of the course. But here's a quick summary. The way this typically works is you as a user call the execute template method on an async task. And what execute does is it collaborates with a couple of other threads and a couple other parts of the async task framework to go ahead and run certain hook methods at certain points in time. The first thing that gets called in the UI thread is something called onPre-execute. And this hook method is used to perform various initialization activities, popping up a dialog, for example. Then, in a separate thread that runs independently of the UI thread, long-running operations can take place via the doInBackground hook method. And this is something you would typically fill in to carry out the long-running operations. You don't want blocking the UI thread. And when the doInBackground method is finished, it goes ahead and returns a result, which is called back in the context of the UI thread via the onPost-execute hook method. And this is where you typically do any cleanup or display operations. You might display the results of the long-running computation in the UI, which is perfectly fine because now you're running back in the context of the user interface thread again. If you take a look at this URL, you'll find out lots more about the async task framework. And I also encourage you to take a look at the source code in Android. There's some really interesting programming techniques and patterns and idioms that are used to implement async task. Another way to do things in Android is called handlers, messages, and runnables. That's another way for threads to communicate. And here's the typical way in which this is used. The user interface thread in Android is typically dedicated to certain kinds of operations, interacting with the user, handling various callbacks from the system, dealing with various lifecycle methods on activities like onCreate, onDestroy, onStop, onStart, those kinds of things. That's what the UI thread does. And what it does is it contacts a mechanism called the looper to manage the dispatching of entries that show up in a message queue. Every looper thread in Android has a message queue, and the UI thread is a looper thread. And this message queue can then be used by other threads to communicate with the user interface thread. If you take a look at this URL, it describes the basic ideas and the idioms and patterns that are used to program this part of Android. So going along with the UI thread are these abstractions called handlers. And handlers are typically used in various ways, but one way to use them is to have background threads that are not the main UI thread that do long-running computations. And when they are done, they use a handler in order to communicate their results in a way that shows up back in the user interface thread. So for example, there's a couple different ways to do this. One way to do it is to have a background thread send a message through a handler, which will then show up in another thread. For example, the UI thread by default, although you can have other non-UI threads working in the same kind of manner. Let's focus on the UI thread, though, just to be specific. So in this case, when you send a message through a handler, that ends up being enqueued in the UI thread's message queue, which is part of the looper. And then as the UI thread loops back around again and gets the next message, it will go ahead and dispatch that message through a handle message hook that it uses that you can override to customize the way in which those messages are processed in the context of the UI thread. Likewise, you can also go ahead and basically enqueue or post runnables with a handler. And those end up being dispatched in the UI thread or whatever thread the handler is associated with so that their run methods get called back in the context of the UI thread. So yet another way to be able to pass information from a background thread to get it to do something interesting in the UI thread. There's lots of other descriptions here at this particular website describing other ways of programming the various background processing and threading and so on in Android. Very useful set of tutorials here. So to summarize this part of the module, Android provides a wide range of concurrency mechanisms that applications can use to run different operations concurrently within a process, within an application. Some of these mechanisms are the kind of stuff you'd find if you were a regular Java programmer programming in a desktop environment or a server environment and so on. So it should be very, very familiar to you if you have background with Java threading, Java concurrency, and Java synchronization. Some of the other parts of Android are more idiomatic. They're things that are more specific to the way in which Android handles events and does its user interface processing and so on. These are typically fairly stylized patterns and not hard to understand, but they're not quite as general purpose as what you would find with the Java threads. As I mentioned, there are many patterns that are part of this. The monitor object pattern is a good example of what you find through Java threading. The half-sync, half-async pattern, which is a POSA 2 pattern that we'll talk about later in the course, is a good example of the way in which things like the UI thread communicates with those background threads through the runnables and the handlers and the messages and so on. And you can take a look here at this website, the URL for information about monitor objects and information about the half-sync, half-async pattern. And it's also worth noting that there are a number of very good books that describe Java threading and patterns for Java threading. And even though these books are not specific to Android, you'll find many of the concepts that they describe and the patterns that they cover will be useful for making sense out of how Android does its concurrency as well. There's also a link you might find for an online supplement to Doug Lee's classic book, Concurrent Programming in Java, which has a number of patterns which have also been adopted and used in the context of Android and Android concurrency.